Currently, what is gradient descent and why is it important in machine learning? Gradient descent is an optimization algorithm used to minimize a cost function by iteratively updating model parameters in the direction that reduces error. It is essential in machine learning because it allows models to learn by finding the optimal set of parameters that improve predictions. So can you explain how gradient descent works in simple terms? The gradient phase space and descent works like a ball rolling downhill to find the lowest point, which represents the minimum error. It calculates the slope gradient of the cost function and updates the parameter step by step in the direction that reduces the error until it reaches the lowest point. What is the difference between batch gradient descent, stochastic gradient descent, SGD and mini batch gradient descent? Batch gradient descent uses the entire dataset for each update, which is stable but slow for large datasets. Stochastic gradient descent updates the model using one data point at a time, making it faster but noisy. Mini batch gradient descent strikes a balance by using small subsets of data mini batches for each update, combining speed and stability. Hugging Face faces that how do you choose the learning rate for gradient descent and why is it critical? The learning rate determines the size of each step during optimization. A proper learning rate ensures steady progress toward the minimum error. If it is too high, the algorithm may overshoot and fail to converge. If it is too low, the process becomes slow and inefficient. Faces that can, what are the consequences of using a very high or very low learning rate in gradient descent? A very high learning rate can cause the model to oscillate around the minimum or diverge entirely, while a very low learning rate makes convergence extremely slow, possibly getting stuck in local minima or suboptimal solutions. Can you explain that? Can you the concept of a cost function and its role in gradient descent? The cost function measures the error between the model's predictions and the actual target values. Gradient descent minimizes this cost function by adjusting the model's parameters and guiding the model toward better predictions. What it says that what is the difference between convex and non-convex cost functions and how does it affect gradient descent? A convex cost function has a single global minimum, making optimization straightforward. A non-convex cost function, common in deep learning, may have multiple minima and saddle points, making it harder for gradient descent to find the global minimum. What are the advantages and disadvantages of stochastic gradient descent compared to batch gradient descent? Stochastic gradient descent is faster and can escape local minima due to its randomness, but it produces noisier updates. Batch gradient descent is stable but computationally expensive for large datasets. What is gradient explosion and how can it impact the optimization process? A gradient explosion occurs when the gradients become excessively large, causing instability and erratic updates during training. This can prevent the model from converging and lead to numerical errors. What is the vanishing gradient problem and how does it affect model training? The vanishing gradient problem occurs when gradients become very small, slowing down or stopping the learning process, especially in deep networks. This can prevent the model from learning effectively. Hugging Face spaces that can, how do techniques like learning rate schedules or adaptive learning rates improve gradient descent? Can learning rate schedules gradually reduce the learning rate during training, preventing overshooting? Adaptive learning rates, like those in Adam and RSprop, can dynamically adjust the learning rate based on the gradients, improving efficiency and convergence. Hugging spaces that can. What are some commonly used optimizers that are based on gradient descent? Last but can common optimizers, stochastic gradient descent, SGT, ADAM, RMSprop, and ADAGRAD. These methods the performance of gradient descent by incorporating techniques like momentum or adaptive learning rates. How does the ADAM optimizer improve upon traditional gradient descent methods? The ADAM optimizer combines the benefits of momentum and adaptive learning rates. It adjusts the learning rate for each parameter individually, speeding up convergence and making training more reliable. Why is feature scaling important when using gradient descent? Feature scaling ensures that all features contribute during optimization. Without scaling, features with larger ranges dominate the optimization process, leading to slower or less effective learning. What are the challenges of using gradient descent with very large datasets? Large datasets make gradient descent computationally expensive. Mini batch gradient descent and parallel computing with GPUs can help address this challenge, improving efficiency. How can gradient descent handle local minima or saddle points in the cost function? A gradient descent can handle local minima and saddle points by using stochastic methods like SGD or optimizers with momentum, which help escape these traps. What is gradient clipping and when is it used? Gradient clipping limits the size of gains during training to prevent gradient explosion. It is especially useful in deep networks like RNs. Rigging phase. Can gradient descent be used for all types of machine learning problems? Why or why not? Gradient descent is not suitable for problems with discrete parameters or non-differentiable cost functions. For these cases, other optimization methods like genetic algorithms may be needed. How do you determine convergence in gradient descent? Convergence is determined when the cost function stops decreasing significantly or when parameter updates become very small. Monitoring validation performance is also helpful. Why might gradient descent fail to find the global minimum, and how can this be litigated? Gradient descent may fail to find the global minimum in non-convex functions due to local minima or saddle points. Using advanced optimizers, random restarts, or better initialization can mitigate this issue. Can you explain the role of initialization in gradient descent? A good initialization accelerates training and helps avoid poor convergence. Poor initialization can lead to slower optimization or getting stuck in suboptimal solutions. What is in space that can the relationship between epochs and iterations in gradient descent? An epoch refers to one complete through the dataset, while an iteration refers to a single update to the model parameters. For mini-batch gradient descent, multiple iterations occur within one epoch. How does the choice of a loss function affect gradient descent? The loss function defines the optimization objective. A well-chosen loss function aligns with the task, e.g., cross entropy for classification, and ensures effective learning during gradient descent. Spaces they can. How does the choice of batch size influence the performance of gradient descent? As small batch sizes lead to noisier but faster updates, while large batch sizes produce smoother updates but require more memory and computational power. Hugging spaces that can. What are some practical techniques for speeding up gradient descent in large-scale machine learning problems? Techniques include using mini batches, leveraging parallel processing with GPUs, and implementing optimized libraries like TensorFlow or PyTorch. What is the role of regularization in gradient descent and how does it influence optimization? Regularization adds constraints to the cost function to discourage overly complex models. This improves generalization, reduces overfitting, and makes gradient descent focus on simpler solutions.